Okay, picking up where we left off. So let me remind you of the problem. So here's the problem. I have a moon, my awesome moon model with the back size blank because it's really old before we knew it was on the back. I have my 100-kilogram object. It starts a distance of 3 moon radiuses from the center, and then it falls down to 2, and I want to find out how fast it's going. So that's the goal. It starts from here and goes. It doesn't make any sound because it's an air thing, and it doesn't make any sound. Okay, so there's my object on a stick. So that's where we're at right now. So in the previous 2 episodes, I calculated. Let me put my moon up. It's very valuable to me. Okay. In the previous 2 solutions, I solved this problem. The first time, I said, okay, here's my object going from position 1 to 2. The gravitational force is not constant, so I just found the average force. And then I didn't know the time interval to use momentum principle, so I did a little math, and I got it anyway. And I got 1,009 meters per second. Okay, but that's assuming an average. I calculated the force at the top, force at the bottom, and the average, which is wrong. The second step, I made a numerical calculation. So I broke this into a whole bunch of tiny time steps as it goes down here of 1 or 10 seconds. And then for each of those time steps, I assumed a constant force, which is a much better assumption. And then I modeled the motion of that thing as it went down, and boom, there we are. Okay, so now we're going to do it another way, the third way. And the third way is going to use the work energy principle. So the work energy principle says that the work is the change in kinetic energy, where the work is F dot delta R, and kinetic energy is 1/2 mv squared. Okay, so that's the work energy principle compared to the momentum principle. The key difference here is that this does not deal with time, so it's actually really great for this situation. We don't know what time is, don't care what time is. Okay. Now, we do have a problem though. We still have a problem. Okay, the first thing is what's F dot delta R? So this is the dot product. So if I have F is some vector Fx, Fy, Fz, and delta R is, let's call that dx, dy, dz. Probably shouldn't use those. Then F dot delta R, the dot product, I take the x components of the 2 vectors and I multiply them together. I add them to the y components multiplied by together and the z components. And we're in an easy situation here, but I want to show you what it is. So this would be fx dx plus fy dy plus fz dz. So this is a scalar value. Okay, so the work is a scalar value, energy is a scalar value. The velocity of the object is the magnitude of the velocity. Can't square a vector. Okay, so I can calculate the force on the object up here. I can use delta R to find the work done, and I could use that to find the change in kinetic energy, but I can't. There's a problem, and I'm gonna fix the problem. Okay, the problem is still I have a non-constant force. It's a non-constant force, so how do I deal with that? And you might have already guessed it. I'm going to break the problem into pieces. Okay, so let's do the following. Let's say that I drop the ball with a constant force. I'm going to find out how fast it's going. And in fact, this case, I'm going to have a ball moving a distance. It's already started moving. Okay, so here's my ball. I have some gravitational force on there. And it's going to come down here. So this is delta R. And this is V1. And this is V2. As vectors, as scalars, because no one cares about vectors right now, because this is a scalar problem. Okay, so how do I use my work energy to find that? The first thing I'm going to do is say, what is my system? I have to write that more clearly. You know what I'm looking at right now when I look at the camera? The lighting is terrible. I need like shade to block my shiny head. I should have fixed that. I've been doing videos for a long time. Okay, so my system is just a ball, or the mass. I'll just call it a ball. It's not actually a ball. That's important because if I have just the ball as my system, then I'm going to have work done by gravity. So the work done by gravity in this case is going to be F dot delta R. Let's say F is going to be equal to 0. I'm going to use, let's use negative mg for now, which is the gravitational force as constant. That's what it would be on the surface of the Earth. And that's fine, 0. And then delta R is going to be equal to 0 delta y, 0. So it is actually moving down. Delta y is in fact negative. Okay. So now if I take F dot delta R, I get 0 times 0, which is 0. I get negative mg delta y plus 0. And that's going to be equal to the change in kinetic energy, 1/2 mv2 squared minus 1/2 mv1 squared. And I want to solve for v2. You'll notice right now I already have a pretty easy equation, right? Because that's way simpler. There's no time in there, so it's going to be a lot easier than the previous case. So let's just add v1, 1/2 m. I can divide by the mass and add 1/2 v1 squared to both sides. So I get 1/2 v1 squared minus g delta y equals 1/2 v2 squared. Now this is a positive number. Okay, so this means v2 is going to be greater than v1 because delta y is negative. It's moving down. So now if I multiply by 2 and take the square root, v2 is the square root of v1 squared minus 2g delta y. And there I have my velocity after that time interval with a constant force. So, does this give you an idea of how we're going to solve this problem? Because we have a non-constant force. So that means that I'm going to break this into a bunch of steps. And during each one of those steps, I'm going to calculate the velocity at the end. And then just keep doing that. Okay? So I'm going to do the work energy problem a whole bunch of times. It's a lot like the numerical calculation for momentum principle, but it's going to be a little bit different. So in each step, I'm going to make a loop of position. I'm going to do this until I get to y is 2r. I'm going to start at y equals 3r. And I'm going to calculate F. Because each time I move down, the gravitational force gets a little bit bigger. And then I'm going to use that, F, to calculate the work. Well, I can really just do this, right? Except here I'm going to have, instead of G, I'm going to have F over M. So I can change that to F over M. That's my force that changes. So I can just say, calculate V. Calculate V2. Update the position, which is Y. And then just keep doing that. Keep doing that, and then at the end, I can print out the velocity. And we're going to do that right now on the computer, switching. Okay, here we are. So I'm starting with my previous problem so that I have some things in there. I'm just going to start deleting some stuff though because we don't really need it. Okay, so I don't need all this for stuff. I'm going to get rid of the loop. We can print out the time if you want. No, we don't really need it. Should I print out the time? The time's a little bit more complicated conceptually to calculate, so let's do that. So there. Okay, now I do need my starting position. Let's just say y equals 3 times r. I need that. I need my starting velocity. I'm not dealing with momentum anymore, so I'm going to say v equals 0. Okay, now I need my dy. How big of a step am I going to take? Let's say dy equals 1 meter seems a lot. I'm just going to go with 10. I just picked that. Okay, I think I'm okay. So now I'm going to say while y is greater than 2 times r, right? So that's going to keep on doing this loop until I get down to 2 times the radius of the moon. First step, calculate the gravitational force. So I only need the magnitude. So I can say gf equals g times mass of the moon times the mass divided by y squared, right? Because y is my distance from the center of the moon to the object. So that's my r. I'm using y for r. Let me look back. Let's see. Yeah, calculate v. So Now I already calculated that equation, so I can just say the new v is the old v. It's going to be the square root of the old v squared, minus 2 times f times dy over m. And now actually I'm going to change this to plus, because my dy is actually negative. I'm moving down 10 meters. So that's my new velocity. It's pretty easy. Okay, and then I'm going to update my position. Y equals y minus dy. See, again, I need minus dy. I think that's it. I really think that's it. But I'm kind of afraid now, so let's... I feel like I made a mistake. Okay, so let's save this, and I'll give you the code. I print the velocity. I need to change this. There is no p, so just print v. Let's run it. I'm scared. Oh, what the heck? It worked. 969, which is actually the same as what I had before when I had it at 1 second time step. Let's change this to 50 meter time distance step. See how much it changes. Okay, that's fine too. Okay, so 50 seems to be fine, because if I change it down to 10, it's fine. Okay, pretty happy with that. I'm so happy I'm going to make a graph, because that's what I do. Okay, t graph equals graph, x title equal, no, I can't spell. Title equals we're going to have position. You could change this to do time too, and that's something that you want to think about. Y title is going to be equal to, let's say, the velocity in meters per second. And then F1 equals G curve, color blue. I like blue. And then down here, I'm going to say F1 dot plot Y V. Yep. Okay, run it. There you go. And let's see, how do I move this? Well, you can't see the whole thing. Let's see. There you go. Okay, great. Okay, now you may think, oh, it's slowing down. No, it's not. It's speeding up, because this is position. This starts here, and then it starts moving this way, right? Because this is not time, this position. This is getting smaller and smaller position. But you can see that actually it does increase at a fairly constant rate the closer it gets, because gravitational force doesn't change as much. Okay, overall, pretty happy. Good thing. Okay, that's version number 3.